Hi everyone and welcome back. This is Module 2, Lesson 2, UAV-derived products. Again, this is Jacob Draper with NAU. So in the first lesson of Module 2, we talk about what the different types of drones are. We also talk about how to set ourselves up nicely for a safe flight. In this lesson, I want to talk about what exactly we do with those images that we collect and see what we can create out of those. So a popular question that I often get is drone imagery really that much better than what's available? I mean, is it better than Google Earth? What about the other satellites that are out there that collect imagery daily? Is drone imagery worth it? Is it worth the investment? So to kind of answer that question, here on the left is a screenshot that I took from Google Earth. This is the track at Cesar Chavez High School in the Phoenix area. And on the right, we actually flew over their football field. This was right before COVID really impacted us in the beginning of 2020. And if we compare these two, it's pretty easy to tell that the drone imagery is far better resolution-wise than what is currently available through Google Earth. Now, I know that Google Earth is not always the best imagery that's available out there, so I went ahead and compared NAPE imagery. NAPE imagery has a 1 meter resolution, and that is on the left here. We are at different scales, 1 to 500 and 1 to 200, but the imagery here on the right hand side is the actual imagery that we collected from the project site. And again, there's a huge difference between 1 meter resolution and the resolution that we ended up with from the project site, which was about 3.2, 3.5 centimeters per pixel. That means whenever we zoom in to those pixels, which look like squares, each one of those squares represents about 3 centimeters versus 1 meter that we would see through NAPE imagery. So before we dive more into the actual images themselves, I want to ask you guys if you know what a point cloud is. So a point cloud is a set of 3D points that help to reconstruct the object or the model that we're looking to obtain. Each one of these points represent an X, Y, and Z position, so that's you can think of left and right, up and down, and Z being our altitude. They also contain color information, and all of that is stored for each point in what we refer to as the densified point cloud. Now, the reason I'm talking about the point cloud first is because I'm kind of going through this in the order of which we process our imagery. And so we upload our images into a software, a photogrammetry software that is called Pix4D. And the first step is basically creating these automatic tie points. And so from those automatic tie points, we end up creating our point cloud. And again, the point cloud is a set of 3D points. So this is not actually a picture. This is not actually images that are stitched together. We are looking at hundreds of thousands of points here that are accurately displaying three-dimensionally the landscape of our project site. Here is a point cloud of a saguaro that was out on the project site. This was about 500 pictures and everything was stitched together and a point cloud was produced. Now, the cool thing about point clouds is, again, it's three-dimensional. So in Orthomosaic, we can really see a lot of definition. We have great resolution. We can have an entire, 1,000 acre project site displayed in one image. But a point cloud is 3D, so we can move around the saguaro. We can see all of the details. We can take accurate measurements. And one of the cooler things is that we can actually take volumetric measurements. So say we decided that we wanted to see how much erosion was taking place in a gully on the project site, we can actually do a cross-section analysis on a drainage and see how much material or how much soil has been moved or eroded over time. And so that is one thing that we can do with a point cloud that we cannot necessarily do with an orthomosaic. Now, I mentioned orthomosaic a few times. What exactly is an orthomosaic? So orthomosaics are basically what I alluded to in that Saguaro slide, where we're taking all of our photos and we're stitching them together to create this large picture that we refer to as an orthomosaic. Orthomosaics are an accurate representation of Earth's surface, having been adjusted for topographic relief. So a lot of times what we have out on the project site is ground control points. They look just like targets, and these are surveyed monuments that we use to georeference our imagery so that it does accurately represent Earth's surface. Now, if we look at this example in the picture here on the right, we can see that 437 images were captured. Well, instead of looking through each of these images to try to find what we're looking for, we can go over to the right to see our orthomosaic and then display our entire project site, zoom in where we want to, and see everything as a whole. So a piece of this might look a little familiar. This is actually the orthomosaic that we produced from the track at Cesar Chavez High School in Phoenix. Looking at this from this scale, it may not seem as though it's super accurate. However, if you zoom in, like you saw in the long jump pit, we can actually see footprints, which is way better than anything that we can see in satellite imagery that is currently available. And I threw this back up here just one more time, just so we can see that on the left is Google Earth, on the right is actually what we captured. This is blown up so that we can see a little bit more fine scale than what we can see on the ortho at that previous scale. So again, it's much more spatially accurate, and we get a lot more detail that would otherwise not be present in satellite imagery. So why do we care about orthomosaics outside of the fact that it is an accurate representation of Earth's surface and that we can take measurements? So like I said, one of the big benefits of an orthomosaic is our ability to measure true distances. Again, we're capturing this entire project site with great detail. We can use orthomosaics to help model buildings, rock faces. For those of you that might be interested in civil engineering, I know that at my former employer, we would use drones to survey side cuts alongside the road. And so with using drone technology, we were able to identify fractures throughout the rock, weak spots, and so that was a huge bonus to having drone technology and the ability to have orthomosaics incorporated into our engineering practice. We use orthomosaics for agricultural assessments, natural resource monitoring. As you can imagine, that's what we're doing with the Lower Salt River Restoration Project, but really what matters the most is that we're seeing the big picture without having to thumb through a bunch of images and without having to look through some of that, I'll say, crappy imagery that's available through satellites. Now I want you all to bear with me. This may just be one still picture, but let's envision that this is actually an orthomosaic, a bunch of images that were stitched together to create what we're looking at here. Now, how would an orthomosaic be beneficial to mining? Well, it's a progress shot, so we can see where we're at this moment in time. We can identify safety hazards if maybe something is failing, a piece of equipment. We can see maybe here on the road on the right, we see that water's pooling up. Maybe there's a couple cracks in that road. We want to make sure that those are addressed so that it's not a safety concern. When it comes to mining operations, orthomosaics are huge because we're able to see the big picture. We're able to identify any health and safety risks, and we can see where we're at and if we're on track for where we envision we were supposed to be. kind of ties right into mining, but construction is another huge one where drones are being used. You can imagine if you were responsible for these high rises going up, that you want to make sure that you're on track to meet your goals. And so being able to fly the project site very quickly, be able to stitch these photos together, make sure that we're identifying our safety hazards, but also make sure that everything is going where it's supposed to be. Again, it's all an accurate representation of Earth's surface, so we can confirm that everything is where it's supposed to be before we get too far ahead of ourselves. Solar inspections is probably one of my favorite uses of drone technology. Prior to drones, the method of going to inspect solar fields was a person driving around and walking and using essentially a heat gun to measure the surface of these panels to see if any of them were failing, and then have technicians go out to repair that panel. While using drones, we can use a thermal camera or a thermal sensor. We can fly the entire solar field, be able to pick out these panels that are defective, and then have technicians go out and replace them. This is extremely time efficient and it saves a lot of money. Agriculture is a huge one. This is kind of similar to what we're doing with Green Drone Arizona. So what we're looking at here is an NDVI view. This is the normalized difference vegetation index. So what we're looking at is these red spots would be the drier or more dead vegetation. We can see that a lot of these red spots are where tire tracks are, and maybe on this right hand side where there's a lot of red, maybe that's where they're mixing herbicide or pesticides, or maybe there's a lot of vehicle traffic in that area. Maybe it's just not getting enough water. Maybe it's a little bit more elevated than the rest of the field here. And then green is showing where our healthy crops are. And so this is a big deal if you're operating a farm, because you can make these corrections before it's a problem. Saves you time, saves you money, and it also makes you more money. All right, so what are digital elevation models? Can you think of what those may look like? So a digital surface model is a type of digital elevation model. A digital surface model, or DSM, is a representation of varying elevation changes related to the surface of a study area. This image here on the left is a piece of our project site on the Lower Sloat River, and what we're looking at is obviously a bunch of different colors, but the red on the left side of the image dictates higher elevation for vegetation. So this might be our taller trees. And then as we move over to the right-hand side of this image, we see we have a lot of green. That's going to be low-lying vegetation. And then up in the top right-hand corner, we have a lot of red, and that is because there's actually a hill. And so we can see a difference in elevation change across the site. But again, this does incorporate vegetation. Now you may have been wondering, well, is there any way we can just look at ground surface without the vegetation? Yes, that is called a digital terrain model, and this is a representation of the ground surface. This is actually a digital terrain model of our project site, and this kind of shows the difference in ground surface elevation across the site, with the kind of whitish being higher in elevation and the green with being lowest in elevation. So we have point clouds, we have orthomosaics, and we have our digital elevation models. But why do we really care about them? So again, orthomosaics are an accurate representation of Earth's surface. This is a screenshot that I took out of our most recent orthomosaic. You can see it's very spatially accurate. We have great resolution. So that increase in spatial resolution allows us to track vegetation populations across the site. That is our goal. It's not the only goal or purpose of having an orthomosaic. This is just what we are using it for. So an orthomosaic provides us with an opportunity to inventory plant species across the project site, which helps us determine if our management efforts are successful and where they can be tweaked. Our DSM and our point cloud, again, this is just for what we are using these products for, but we can use them to analyze canopy height, canopy density, the health of vegetation, the growth stage, and the volume of biomass that's above the ground surface on the project site. We can also use this, like I said earlier in the point cloud slide, we can use this to determine the amount of sediment that has eroded in certain parts of the site. And so this is what we are currently using digital surface models and our point clouds for. Our digital terrain model and digital surface model in conjunction with each other. This image here on the left is what our first year of interns, this was one group's capstone project. They wanted to look at hydrology as a piece of their project, and so they used the DTM to perform hydrology modeling so that they could better predict where shallow micro aquifer sites might be. And honestly, they're pretty accurate. In these areas where we have blue that's not actually the river, but actually inland, we can reach water in about 4 to 5 feet in most of these places, and this allows us to actually go out and plant trees in these areas, and that way they have access to water. So I know that this may have been a little quick. I know it was also brief. We are going to dive very deep into UAV-derived products in Module 6, and so the purpose of this lesson was just to introduce you all to these concepts, get you thinking about it. If you have any burning questions in the meantime, feel free to reach out to Justin or myself. We're always around, we're always willing to help, and we're here for you guys. So in the meantime, enjoy some of the activities, and we'll see you all in Module 3.